Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Sciences, SOS, Master's Degree Programs, M.Sc, Chemistry, MSCCHEM, First Year, MCH 01 to Stereochemistry and Reactive Intermediates, Block-1 Stereochemistry-I, Unit-1 Molecular Symmetry and Chirality, 1.1 Introduction. You have studied in your undergraduate classes that stereochemistry involves the study of arrangement of atoms of a molecule in three dimensions. The two important aspects of stereochemistry are stereoisomerism and the stereochemical changes which occur during a chemical reaction. Broadly speaking, the isomerism is of two types, viz., constitutional and stereoisomerism, and the compounds showing these types of isomerism are called the constitutional isomers and stereoisomers, respectively. The constitutional isomers differ in their bonding sequence and the connectivity of atoms. Just to recall the type of constitutional isomers, which are chain isomers, position isomers, and functional isomers, and three special cases, viz., metamers, tautomers, and ring chain isomers. We would not discuss these types because it is expected that you have a fair knowledge of the same. In contrast to the constitutional isomers, stereoisomers have the same bonding sequence, but they differ in the orientation of their atoms in space. Although you have studied these isomers also in your previous classes, yet we will study more about these isomers in this course. We would start with describing the representation of molecules into dimensions, as it is not always possible to visualize and explain the stereochemical structures in three dimensions. Then we will study about the classification of stereoisomers. The focus would lie on the reasons of existence of optical isomers, i.e., absence of symmetry elements, would be described in detail. The unit deals with another important aspect of optical isomerism and the optical isomers, which is chirality. How does chirality relate to asymmetry would also be elaborated. The concept of chirality will be extended further to compounds with more than one chiral carbon atom in the next unit. Expected learning outcomes after studying this unit. You should be able to draw the organic molecules by different projections and explain the stereochemistry of the molecule, classify stereoisomers and explain the different types, describe different types of symmetry elements, explain the relationship between symmetry and the molecular properties, define chirality and explain the existence of chirality in molecules with one chiral center, and explain the relationship between chirality and symmetry. 1.2 Representation of organic molecules into dimensions. The stereochemistry of organic molecules can be well understood with the use of models that give us a three-dimensional view of a molecule. However, the models are not always available or handy to study the three-dimensional structure of molecules. Therefore, it is important to learn the ways of representing the three-dimensional structures of these molecules on a two-dimensional surface like the paper or a blackboard or a whiteboard. It is necessary to learn that how to draw three-dimensional structures on a two-dimensional paper. Drawing of structures of molecules in such a way is called projection. There are 5 well-known methods for representing the structures. These are divided into following two main categories. Perspective type, this includes the flying wedge and the zigzag representation. Projection type, this includes the fissure, the Newman and the Sawhorse projections. The two types of representations of the organic molecules are described in the following subsections. 1.2.1 Perspective representation of molecules. The perspective type representation includes the flying wedge and the zigzag ways as mentioned above. The two types are explained in the following paragraphs. Flying wedge representation. You know that the valency of carbon is 4, and a saturated carbon atom is attached to 4 groups when joined by single bonds. In flying wedge formula, the 2 bonds of the carbon atom are shown on the plane of the paper, and of the other 2, one is shown above the plane and the other below the plane. The bonds which are in the plane are shown by ordinary lines, but the bond above the plane is usually shown by a solid cone, and the bond below the plane is shown by a broken line. For example, methane can be represented by flying wedge structures as shown in Fig. 1.1 given below. Fig. 1.1, the flying wedge representation of methane. Similarly, the two isomers of lactic acid can be drawn as shown in Fig.1.2. Fig. 1.2, flying wedge representation of lactic acid. The flying wedge formula or three-dimensional representation is usually done for molecules containing chiral centers. It may also be used for achiral molecules. Zigzag representation. The perspective zigzag structure was devised by Masmune. While drawing these types of structures, carbon and hydrogen atoms are not shown. Carbon atom is considered to be present at the junction of two lines and at the end of the line, whereas number of hydrogen atoms is considered such that the valency of carbon is satisfied. Any other atom, if present in the chain, is written there. Any substituent or functional group is written at the appropriate carbon with the help of a bond. This representation always denotes a staggered conformation. The flying wedge and zigzag representations of D-glucose are given in Fig.1.3. You should be able to note the difference between these two. Fig. 1.3, flying wedge, A, and zigzag, B, representation of open chain D-glucose. Remember that a zigzag formula does not represent an eclipsed conformation. 1.2.2 projection representation of molecules. The projection type representation includes the Fisher, the Newman, and the SOS projections as mentioned above. The three types are explained in the following paragraphs. Fisher projections. Fisher projection is a convention for displaying the three-dimensional configurational relationship of a molecule in planar representation. In this representation, the molecule is so oriented that the carbon atom is in the plane of projection, could be paper or blackboard, and the four bonds are shown by two vertical and horizontal lines which intersect each other. The point of intersection of these lines represents the carbon atom. The horizontal lines of the cross represent bonds projecting outward I above the plane, and the vertical lines represent the bonds going below the plane. Fig.1.4 represents a general molecule drawing in wedge formula and its equivalent in Fisher projection. The two groups X and Z are on the plane of paper in wedge and dash representation, and the projection is shown under it. For drawing the Fisher projection, a molecule may also be viewed as shown in Fig.1.5 and then writing groups C and D on the horizontal line as they are projecting out of the plane towards viewer. Fig. 1.5, viewing a molecule for Fisher projection. Fisher projections are normally used to represent compounds with chiral centers. For example, one of the isomers of lactic acid can be drawn in wedge and dash formula as 1.6, A, whose Fisher projection is shown as 1.6, B. Fig. 1.6, lactic acid, A, wedge and dash, B, Fisher projection formula. We can actually draw many Fisher projections for any stereoisomer because it depends upon the direction of viewing the molecule. As an example, the above stereoisomer of lactic acid can also be represented in different ways. One can represent complicated carbohydrates like glucose and fructose, etc. in a way that communicates their stereochemical information by adhering to the specified guidelines for drawing these projections. SOS projection. In this projection, the two key carbon atoms are joined by a diagonal line which is taken to be on the plane of the paper, and the remaining bonds are shown by small lines projected above and below that plane. There is a free rotation about C to C bond, and the three groups attached to one carbon may be rotated clockwise or anticlockwise in relation to the three groups attached to the other carbon atom. The relative position of various groups attached to these carbon atoms can be easily represented by this type of projection. For example, N-butane, CH3CH to CH2CH3, can be represented as shown in Fig. 1.8. Fig. 1.8. SOHOS representations of N-butane, Newman projection. For this type of projection, the molecule is viewed along the bond joining the two carbon atoms. The carbon atom at the back is represented by a circle, whereas the front carbon atom is represented by a dot at the center of the circle. The three groups attached to the front carbon atom are represented by three lines emerging from this point. The circumference of the circle represents the back carbon atom, and the three substituents attached to this carbon are shown by three lines emerging from the edge of the circle. These straight lines which represent the bonds are drawn at angles of 120 O. Newman projections are helpful for a better visualization of different conformations of a molecule. For example, the staggered conformation of ethane can be drawn in Newman projection as shown in Fig. 1.9. Fig. 1.9. Newman projection of staggered conformation of ethane. Another example is the staggered conformation of butane that can be represented in SOHOS projection and Newman projection as shown below. Some of the important points in the context of representing the molecules in two dimensions are mentioned below. The flying wedge and zigzag formulae have the advantage of showing the molecular backbone in the staggered conformation and entirely on the plane of the paper. Fisher formulae depict the molecule in the unrealistic eclipsed conformation, while the Newman and SOHOS projections show the molecules in their staggered as well as eclipsed conformations. The flying wedge and zigzag formulae are useful to show the actual conformation and configuration of compounds having two or more chiral centers. Newman and SOHOS formulae are most useful for compounds having two chiral centers. When solving the stereochemical problems, sometimes it is essential to convert one representation into the other as a particular form is not able to provide the required information. We would explain the interconversions of various representations of molecules in the following subsection. 1.2.3 Interconversions of projection formulae. A few of the simple ways of interconversion of projection formulae from one to the other form are discussed below. Fisher projection to SOHOS. The conversion of Fisher projection to SOHOS projection in eclipsed conformation and then converting it to its staggered conformation with proper numbering of carbon atoms is evident from the examples given in Fig. 1.11. Fig. 1.11 a represents an isomer of 2,3-dibromobutane in Fisher projection. If its SOHOS form is written keeping C2 in front and C3 at the back, then the eclipsed SOHOS form becomes 1.11 b. Its staggered conformation is represented as 1.11 c, which is obtained by rotation across the bond between C2 and C3. Fig. 1.11 Conversion of Fisher projection to SOHOS, SOHOS to Newman to Fisher. The vertical bonds in the eclipsed form of Newman projection may be arranged in such a way that they remain below the horizontal plane shown by dotted line. The transformation to Fisher projection is then carried out, keeping the front chiral atom as the lowest chiral center on counting from the top in the Fisher projection as depicted in Fig. 1.12 Fig. 1.12 Conversion of SOHOS projection to Newman to Fisher. Fisher to Newman to SOHOS. Fig.1.13 shows the conversion of Fisher projection of a molecule into Newman projection and then into SOHOS projection. Fig. 1.13 Conversion of Fisher projection to Newman to SOHOS. Fig. 1.14 a shows the Fisher projection of one of the isomers of threose carbohydrate. It can be converted into SOHOS form in eclipsed conformation. Fig. 1.14 b. Its staggered form is represented as 1.14 c, which can be converted into Newman projection as in 1.14 d. After having a clarity of the representation of the organic molecules and their interconversion, we proceed to recall the types of stereoisomers. In other words, we will study the classification of isomers in the next section. 1.3 Classification of stereoisomers. The study of the three-dimensional structures of molecules helps to understand their stereochemical relationships. It is very well known that stereoisomerism exists due to the different spatial arrangement of atoms in a molecule, i.e., their three-dimensional structure. The different three-dimensional structure changes into different stereoisomers. The stereoisomers are classified into two types, viz., configurational and conformational isomers. Configurational isomers are the molecules which have different arrangement of atoms and cannot be converted into each other without breaking a bond. These are further classified as geometrical and optical isomers. The optical isomers are further classified as enantiomers and diastereomers. The conformational isomers are different relative arrangements of atoms obtained by the rotation across single bonds in the molecule. We will discuss about conformational isomers in detail in Unit 3. You have already studied about these types of isomers and also the UPAC notations used in their nomenclature in your previous classes. Now we will discuss more about these types of isomers. We start with geometrical isomers in the following subsection. 1.3.1 Geometrical isomers. The geometrical isomers belong to the configurational type of isomers as mentioned above, which depend upon the configuration of the molecules. Configuration can be defined as the specific arrangement of atoms in space which characterize a particular stereoisomer. In other words, it can be said that the arrangement of atoms that emerges from the spatial arrangement of its bonds. As per EUPAC, 1979. Configuration is defined as the arrangement of the atoms in space of a molecule of defined constitution, without regard to arrangements that differ only as after rotation about one or more single bonds, there are two necessary conditions that are required to be fulfilled by geometrical isomers. 1. There should be restricted rotation between two atoms under consideration. This can be due to presence of a double bond between the two atoms or when the two atoms are part of the same ring. These two atoms may not necessarily be carbon-carbon only and can be carbon-nitrogen or nitrogen-nitrogen also. 2. Each of the two atoms under consideration should have two different groups linked to these. You are familiar with CIS and trans notations for geometrical isomers, which are based on the presence of identical groups on the same or opposite side of a double bond. If any compound contains four different substituents, example, in ABC is equal to CXY, or contains more than one double bond, then it cannot be designated as the CIS trans. In such cases, the E and Z system of nomenclature is used. The concept in brief can be well depicted by the nomenclature followed in case of 2-butene as depicted in Fig. 1.15 Fig. 1.15 Geometrical isomers of 2-butene. You will study more about the EZ notations of geometrical isomers and the CIP rules for assigning priority of groups attached in detail in Unit 5 of Block 2. The following subsection explains the other type of configurational isomers, viz., the optical isomers. 1.3.2 Optical isomers. As per the definition given above, optical isomers belong to the type of configurational isomers. It can be said that the molecules that have the same molecular formula but have a different arrangement of the atoms in space are called optical isomers. However, this is not the complete explanation of these molecules. As the name suggests, these isomers are optically active or show the property of optical activity. Optical activity is a physical property of a molecule like other physical properties, which is defined as the property of molecule to rotate the plane of plane polarized light. However, All the molecules or compounds do not show this property. Then what type of compounds show optical activity? It is essential to understand the concept of plane polarized light to answer this question, and surely you are aware of this concept from your previous classes. You know that a molecule containing a carbon atom attached to 4 different substituents, A, B, C and D, results in the existence of non-superimposable mirror images called the enantiomers Fig. 1.16. If we try to superimpose structures I and II, we get structure 3. It is clear from structure 3 in figure that the structures I and II are non-superimposable. Such molecules are said to contain an asymmetric carbon atom and are known as chiral molecules. Fig.1.16 structures I and II as the mirror images of a molecule with structure 3 depicting the non-superimposability of structures I and II. For a molecule to show optical activity, non-superimposability of mirror images or chirality or presence of asymmetric carbon atom is required. However, it becomes difficult to find out the superimposability of molecules with more than one asymmetric carbon atoms. This raises questions like why some molecules are chiral while others are not. How do we check chirality or asymmetry in a molecule? These questions are addressed by the presence of some symmetry elements in the molecule under consideration. The symmetry is a geometric feature which can be a point, line or plane. The process for finding the presence of any such element in a molecule involves few steps called symmetry operations, which are discussed in following section. 1.4 Symmetry elements and symmetry operations. You have read just above that the symmetry of a molecule is described in terms of symmetry elements. The operations performed to determine the presence of symmetry elements are called symmetry operations. A symmetry element can be a geometric line, plane or point with respect to which one or more symmetry operations are performed. The symmetry elements are of 4 types. These are rotational or proper axis of symmetry, CN, plane of symmetry, sigma. Center of symmetry or center of inversion, I, alternating or improper axis of symmetry, SN. These types are explained in the following subsections. 1.4.1 Rotational axis of symmetry. It is denoted by the symbol CN, Latin word circulate, and is also called proper axis of rotation. The subscript N denotes the fold or order of rotation. It is defined as an unfold axis of symmetry when a structure possessing this axis is rotated by an angle of 360 degrees per n around the axis. The structure which results is superimposable with the original one. It is also called symmetry axis or simple axis of symmetry. The value of n can never be a fraction, because in such a case every Cn operation will not give superimposable structure. That is, equivalent structure. If a molecule possesses more than one simple axis of symmetry with different values on n, then the Cn axis having maximum value of n-fold is called the principal axis. When there are several Cn axes with same value of n, then the principal axis is one that involves maximum number of atoms of the molecule. We consider the example of CIS1,3-dichlorocyclobutane. It can be depicted by its enantiomers as shown in Fig.1.17. Let us see if it has any symmetry element. Rotation by 90° about the axis shown in the figure gives a molecule which is not identical to the starting compound, but a rotation of 180° gives an identical molecule, indicating the existence of a twofold rotational axis of symmetry. 360° 180° is equal to 2. Thus, it has a twofold rotational axis of symmetry. A plane of symmetry is an imaginary plane passing through an object, dividing it such that one half is the reflection of the other half. 1.4.2 Plane of symmetry. A plane of symmetry is a plane such that if a line from any element on one side of the plane is drawn perpendicular to the plane and the line extended to an equal distance on the other side of the plane, an identical element is found at the end of the line. In other words, we can say that one half of the molecule is mirror image of the other half. It is because of this property, a plane of symmetry is also called the mirror plane. It is designated as sigma, that comes from the German word Spiegel, meaning mirror. We find the plane of symmetry not only in organic molecules but in many objects that we see around, example, a butterfly. We see that in the butterfly one half of the body and the wings is identical to the other half. The cube shown in Fig. 1.18 has several planes of symmetry. Both the beaker and the compound, bromochloromethane, have only one plane of symmetry. You might be familiar with the famous Monument of India, Taj Mahal. It is very symmetrical. One half of the building is symmetrical to another half. The plane may pass through atoms, between atoms, or both. For example, 2-chloropropane has a plane of symmetry. Fig.1.19. A. The 2-chlorobutane molecule does not possess a plane of symmetry. Fig.1.19. B. Fig. 1.19. Plane of symmetry in A. 2-chloropropane and B. 2-chlorobutane. Some more examples of compounds having a plane of symmetry can be given to have a clear understanding. These are 1,1-dichloroethene, 1,1,2,2-tetrachloroethene, and molecules with two secondary butyl groups as shown in Fig.1.20. Fig.1.20. Examples of molecules with plane of symmetry. It should be remembered that every planar molecule necessarily has a plane of symmetry, namely the molecular plane. The symbol is usually found to carry three subscripts indicating the position of symmetry plane planes relative to the principal axis, Cn. These are explained below and depicted in Fig.1.21. Horizontal, H, represents the reflection in the plane containing the principal axis of rotation, that is, axis with highest value of n dot. Vertical, V, represents the reflection in the plane containing the principal axis. Diagonal, D, represents reflection in the plane which contains the principal axis and bisects the angle between the two C2 axes. When both alpha V and alpha D planes are present, then the alpha V plane contains the greater number of atoms. 1.4.3 Center of symmetry. Center of symmetry is defined as a point in space such that if a line is drawn from any part or atom of the molecule to that point and then extended an equal distance beyond it, an analogous part or atom will be encountered. In other words, inversion of all atoms in the molecule through the point results in an arrangement indistinguishable from the original one. The point is also called a center of inversion. The center of symmetry is represented as I. All Cn and elements, if present, in addition to I, must pass through I. Let us understand it with the help of a molecule of 2,4-dimethylcyclobutane 1,3-dicarboxylic acid. It has got two carboxyl groups at two positions and two methyl groups at other two positions. Let us focus on the structure for this molecule given in Fig. 1.2. We draw a line from the carboxyl group, pass it through one point as shown in the structure and extend beyond. On doing so, we meet another carboxyl group after the same distance. When we start from the hydrogen, move through the center point and extend this line beyond, we meet another hydrogen. Similarly, for methyl group, we find that after an equal distance, passing through this point, we get a methyl group. Some other examples of compounds which have a center of symmetry are ethane, A, trans 1,2-dichloroethene, B, shown in Fig. 1.23, A and B, respectively. A molecule shown in 1.23, C, contains two secondary butyl groups at 1 and 3 position of a cyclobutane ring, also possesses a center of symmetry. Fig. 1.23. Some molecules showing center of symmetry. 1.4.4 Alternating axis of symmetry. Alternating axis of symmetry is designated as SN. It is also known as improper axis of rotation or also rotation reflection axis of symmetry. A molecule is said to possess an n-fold alternating axis of symmetry if rotation through an angle of 360 degrees per n about an axis followed by reflection in a plane perpendicular to the axis gives the molecule which is indistinguishable from the original molecule. The alphabet N is arrived by the rotation of the molecule. If the molecule is rotated by 90 degrees, the value of N will be 4. Suppose we get the above explained observation after 180 degrees rotation, the value of N will be 2. Hence, we say that the molecule possesses a twofold alternating axis of symmetry or fourfold alternating axis of symmetry if the value of N is 4. When the rotation is by 60 degrees, the molecule is said to possess a sixfold alternating axis of symmetry and so on. We can understand the symmetry operation by taking 1,3-dichlorobutane molecule. If we try a 90 degrees rotation to get the position for a similar group, we will not be able to achieve this. However, rotation of 180 degrees makes this possible. We can say that the molecule has twofold alternating axis of symmetry and not a simple axis of symmetry. Thus, in rotation around the axis, the Cl group appears twice, but one of them appears above the plane of the molecule and the other appears below the plane. You can try to visualize this in Fig. 1.24. Fig. 1.24. Alternating axis of symmetry in 1,3-dichlorobutane. In order to understand the operations, let us consider an isomer of 1,2,3,4-tetramethylcyclobutane that has the methyl groups alternately above and below the plane, structure I in Fig. 1.25. Let us see the result of rotation of 90 degrees on structure I. We get structure 2. The reflection of structure 2 in the plane of the ring gives structure 3, which, if you see carefully, resembles structure I. We can say that the molecule has a 360 degrees per 90 degrees is equal to 4, i.e., a fourfold alternating axis of symmetry. This is depicted in the figure given for this molecule. Fig. 1.25. Fourfold alternating axis of symmetry. The molecule 1, shown in Fig. 1.26 contains 4 sec-butyl groups, each of which contains one asymmetric carbon atom, but is not chiral because it possesses a fourfold alternating axis of symmetry. Structure 2, which is the mirror image of 1, becomes superimposable over it by turning the ring upside down and then rotating it by 90 degrees along the axis shown in the figure. You should try it yourself to show the existence of alternating axis of symmetry. Fig. 1.26. Molecule with twofold alternating axis of symmetry. 1.4.5 The identity element. The identical operation, E, is the process of doing nothing to a molecule, and the corresponding symmetry element is the identity element, E. If no change is made to a molecule or any other object, then it will always be identical to the original structure. So all the molecules and all objects possess the identity element and the corresponding identical operation. 1.4.6 Asymmetric and disymmetric molecules. Chiral molecule exists into stereoisomeric forms known as enantiomers in which the mirror images are non-superimposable with each other. It is clear from the above given description that a molecule would be chiral if it is devoid of symmetry elements, which include plane of symmetry, center of symmetry, and alternating axis of symmetry. It is appropriate to mention at this stage that one-fold alternating axis of symmetry corresponds to plane of symmetry. Similarly, a two-fold alternating axis of symmetry corresponds to center of symmetry. If a molecule contains any of these elements of symmetry, it will be called a symmetric molecule. If the symmetry elements are missing, such molecules were earlier called asymmetric molecules. If alternating axis of symmetry and simple axis of symmetry both are absent, these molecules are called as asymmetric and they are usually active. But if simple axis of symmetry is present and alternating axis of symmetry is absent, then such molecules are now given the name as disymmetric and they are usually active. The general points to remember are summarized below in Table 1.1. Table 1.1 Symmetry designations of chiral molecules. The molecular properties of molecules are based on the molecular structure that is directly or indirectly related to the symmetry of the molecules. You will study about this relationship in the following section. 1.5 Symmetry and molecular properties. The physical properties of a compound are dependent on molecular structure, and to a good extent the symmetry is responsible for the difference in their properties. The properties that are discussed in the following subsections are the ability to rotate the plane of polarized light, the ability to display permanent dipole moment. 1.5.1 Rotation of plane polarized light. You are familiar with the fact that ordinary light consists of oscillating electrical and magnetic fields, or we can say the waves vibrate in all directions, perpendicular to the direction of the beam of light beam. On passing the ordinary light through a device called polarizer, its oscillations in all but one direction are blocked and the light emerging from the polarizer oscillates in only one plane. This is called the plane polarized light. When this plane polarized light is passed through solution of any optical active substance, the plane gets rotated by some angle. The compounds those rotate the plane of plane polarized light to the right are called dextrorotatory, and those which rotate it in the left direction are called levorotatory. You have studied why compounds exist as optical isomers. The answer is known to you. It is because of the chirality in the molecule. You have studied how chirality relates to the symmetry in the molecule. The molecules those are chiral can rotate the polarized light. The property remains unchanged under a proper operation, rotation, but changes sign under an improper operation, reflection. We can say that an improper operation, reflection, transforms one enantiomer into another. 1.5.2 Dipole moment. You know that the dipole moment of a chemical compound is due to a difference in the charge distribution in its molecules, which is due to the difference in the electronegativities of the constituent atoms. The molecule as a whole will have a dipole moment only if the local dipole of a group in one region is not compensated by an opposite local dipole elsewhere in the molecule. Symmetry properties are responsible for indicating whether this will or will not be the case. Specifically, if a molecule has a center of symmetry, then to each local dipole there will be a corresponding equal and opposite one, and the overall dipole moment will be zero. If a molecule has a CN axis, the component of the dipole moment vector at right angles to the axis averages to 0 and the molecule can, at best, have a moment along the direction of the axis. However, this component of the moment will also vanish if there is a symmetry plane perpendicular to the axis or there is at least one other axis perpendicular to the first. 1.6 Symmetry and chirality. You have read some of the important concepts associated with molecular symmetry and symmetry elements. This is very significant as the understanding of symmetry helps to determine whether or not a molecule will be chiral. We will first recall the concept of chirality and then relate it to the symmetry in a molecule. 1.6.1 Chirality. The term chirality has been derived from a term called chiral, and the term chiral is derived from a Greek word chair, which means hands. What has chiral and chirality got to do with the hands? You are familiar with another concept, with non-superimposability. We observe that our two hands are identical, but they are non-superimposable. This property was given the name as handedness or chirality. Thus, chirality is a property exhibited by two substances made up of identical parts, but are not superimposable on each other. The objects which cannot be superimposed on their mirror images are called chiral. Some other examples are hand gloves, screw, scissors. In 1815, the physicist Jean-Baptiste Biot predicted that the ability to rotate the plane of polarization was attributable to some asymmetry in the molecules. Van 't Hoff and Lebel later determined that the molecular asymmetry was associated with compounds having one or more asymmetric carbons. Let us consider some objects which can be superimposable. For example, let's take a chair and its mirror image as shown below. If the mirror image is picked and put it over the chair, it will be exactly superimposable. We can say that the chair is a chiral. Some other examples of this type include letter A, number 8, a butterfly, etc. These objects which can be superimposed over each other are called a chiral. You will be able to appreciate the concept of chirality in organic molecules by taking suitable examples. You have read above that chirality is non-superimposability of mirror images. You analyzed and observed that non-superimposability arises due to the presence of an asymmetric carbon atom or the absence of some symmetry elements. Table 1. 1. Hence it can be inferred that dissymmetry or asymmetry is a necessary and sufficient condition for a molecule to show optical activity and hence optical isomerism. The pair of optically active isomers is called enantiomers. Two enantiomers have identical physical properties, except for the direction in which they rotate the plane of plane polarized light. One rotates the plane of plane polarized light to the right-hand side whereas the other rotates to the left-hand side by an exactly same magnitude. Thus a compound with one asymmetric carbon atom, for example to bromobutane, can exist as two different stereoisomers. Imagine a mirror between the isomers. Notice that they are mirror images of each other which are non-superimposable i.e., they are different molecules. These two are the enantiomers. The molecule has an asymmetric carbon atom which is responsible for the chirality of 2-bromobutane. 1.6.2 Chirality vis-a-vis symmetry elements. Let us now see how the symmetry relates to chirality. By definition, a chiral object is not superimposable on its mirror image, where the mirror image of an object is its reflection. You have read that for any molecule which contains a plane of symmetry, alpha, or the corresponding symmetry operation, the reflection operation, alpha, will superimpose the molecule on its reflection. Thus, any molecule which contains a plane of symmetry must be a chiral. In fact, any molecule which contains an improper axis of rotation, SN axis, will be a chiral. The reason for this is that an improper axis of rotation is the product of a proper rotation, Cn, followed by a reflection, alpha, as dealt in subsection 1.4.4. It was also shown in subsection 1.4.6 that a plane of symmetry, alpha, and center of inversion, I, are just special cases of an SN axis, S1 and S2 respectively. The reflection part of these operations will always cause the molecule to be superimposable on its mirror image and hence, a chiral. This provides an alternative definition of chirality: any molecule or other object which in all accessible conformations do not contain an improper axis of rotation, Sn, N0, is chiral, a consequence of the dependence of chirality on the absence of an Sn axis. That any molecule that possesses an Sn axis, or a plane of symmetry or center of symmetry, will be achiral, and a molecule in which Sn axis is absent will be chiral. Molecules containing a single chiral center are always optically active and lead to a pair of enantiomers. There are compounds which contain more than one chiral center but still are optically inactive. Any pair of configurational stereoisomers that are not enantiomers are classified as diastereoisomers. Enantiomers and diastereoisomers differ in physical and chemical properties and behave as different compounds. We will discuss more about enantiomers and diastereoisomers in the next unit. 1.7 Summary. The unit on molecular symmetry and chirality pertains to the stereochemistry of organic molecules that has direct relationship with the three-dimensional structures. There are two main types of representing the three-dimensional structures of these molecules on a two-dimensional surface, like the paper or a blackboard or a whiteboard. These are perspective type that includes the flying wedge and a zigzag representation, and projection type that includes the Fisher, the Newman and the SOS projections. The interconversion of the projections is essential for getting a required information. Thus, conversion of Fisher projection to SOS and vice versa, SOS to Newman to Fisher and vice versa, i.e. conversion of Fisher to SOS and Newman projections has been dealt by taking relevant examples. The study of the three-dimensional structures of molecules describes the stereochemistry of molecules and their existence as stereoisomers. The stereoisomers are classified into two types, viz. Configurational and conformational isomers. Configurational isomers are the molecules which have different arrangement of atoms and cannot be converted into each other without breaking a bond. These are further classified as geometrical and optical isomers. The molecules that have the same molecular formula but have a different arrangement of the atoms in space are called optical isomers. The optical isomers are further classified as enantiomers and diastereomers. The conformational isomers are different relative arrangements of atoms obtained by the rotation across single bonds in the molecule. The symmetry of a molecule is described in terms of symmetry elements. The operations performed to determine the presence of symmetry elements are called symmetry operations. A symmetry element can be a geometric line, plane or point with respect to which one or more symmetry operations are performed. The symmetry elements are of four types. These are rotational or proper axis of symmetry, CN, plane of symmetry, sigma, center of symmetry or center of inversion, I, alternating or improper axis of symmetry, SN. The identical operation, E, is the process of doing nothing to a molecule, and the corresponding symmetry element is the identity element, E. A molecule contains any of the elements of symmetry, I or Sn, it will be called a symmetric molecule. If alternating axis of symmetry and simple axis of symmetry both are absent, these molecules are called as asymmetric and they are usually active. But if simple axis of symmetry is present and alternating axis of symmetry is absent, then such molecules are given the name as disymmetric and they are usually active. The physical properties of a compound are dependent on molecular structure, and to a good extent the symmetry is responsible for the difference in their properties. Two such properties are rotation of plane, polarized light, and dipole moment. Chirality is a property exhibited by two substances made up of identical parts but are not superimposable on each other. The objects which cannot be superimposed on their mirror images are called chiral. Any molecule which contains a plane of symmetry must be a chiral. In fact, any molecule which contains an improper axis of rotation, SN axis, will be a chiral. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.